Thank you so much for the introduction. Good afternoon, everyone. My name is Felix Heisel, and I will, as mentioned, speak about deconstruction versus demolition using the case study of the Catherine Commons project. I'm pretty sure I don't have to tell you this after the whole morning, but I do like to have a couple, like 5 slides to kind of set the scope in my own words and kind of show the importance of reuse and deconstruction for the built environment. And it starts with the linear economy. As we know, the linear economy is responsible for probably more than 50% of all the resources that we take out of the out of the Earth's crust, more than 40% of solid waste that is being produced, and roughly 40% of carbon emissions. And if we really want to change quickly and stay within the 1.5 degree goal that was agreed on in Paris regarding global warming, then we need to really quickly basically mirror that exponential growth of CO2 emissions and reduce emissions by roughly 65% in the next 5 years, which is an immense undertaking for our built environment, considering the scale, the reach, and the amount of stakeholders that are involved. And we know that 28% come from building operation and 11% come from materials and construction, but that's a perspective on the problem that doesn't take this drastic and quick change into consideration, because if you look at it on a timeline, then actually this relationship changes drastically. I'm sure you've seen these slides all before, but if we build a building today, right, then on day 1 of that building's existence, when you cut that ribbon, the carbon emissions of that building are basically all from the construction. They're all embodied carbon emissions because those are upfront emissions that have been emitted on day 1 of that building's existence. And then slowly over the use time of the building, we have the operational carbon emissions adding up. But so if we remember, we only have 5 years, right? Then the way we built and the materials that we built with have the largest impact on that equation. And so on the left side, you see the buildings that we built with, but maybe more importantly, on the right side, the flip pyramid shows the strategies that we apply to reduce carbon emissions or maintain the carbon that has been emitted already. And that has to do with the end of life of buildings and ideally the prolongation of the use time. So first of all, it's always best to preserve, to maintain. If that doesn't work, you can adaptively reuse, you can overbuild, you can relocate. But what we're not going to do anymore is demolish, ideally, right? And so the last resort before that is the deconstruction, because we can then at least save the materials, save the carbon that is in these materials, and bring them in a different building, in a different configuration into a next use. And so this is one of the focus points that we're looking at the Circular Construction Lab, which, as was mentioned in the introduction, is my research unit here at Cornell University. And the goal really is to have a kind of interdisciplinary group of students. Most of the members of the lab are bachelor and master students from a very diverse range of disciplines, from mycology to architecture to planning to economics. And we're all working on this together to figure out what are ways to close the loop to implement circular economy thinking into the built environment. And so as mentioned, today I wanted to talk about one case study project that we did in the lab. What you see here is an aerial picture of Ithaca, New York. In the middle is Catherine Commons. This is a development on College Avenue, and for this development, 11 buildings from all about 1906 to 1911 were slated for demolition. And so we started a conversation with the developer, and in the end convinced that developer to deconstruct one of these 11 buildings side by side to the demolition of the other 10. And the benefit from an academic perspective is that these buildings were all built identical, right? More or less. So they have the same style, they have roughly the same size. And so we had a really good comparison of the demolition and the deconstruction process. And I'll show you some numbers looking at this comparison in this presentation. But what you also see in this image is simply the status quo. It's one excavator, one person on the side, maybe a second one with a water hose to reduce the dust emissions that come from that process. And the mechanical demolition essentially reduces everything to rubble that is then pushed into dumpsters and shipped off to landfill. The central New York industry here does not believe in source separation. There's very little recycling going on. I know that Canada is doing a better job at that. But just to give you an idea of what the comparison is that we're dealing with here. And so the project had two really important sort of parameters that we negotiated with the developer. On the one hand side, it couldn't cost him more than the demolition would have, and it couldn't last longer than the demolition would. And so those are actually two criteria that make deconstruction really difficult, right? Usually it costs more and it takes longer. And so from the get-go, we had to think outside of the box. What you see here is a panelized deconstruction process, which means essentially that we're cutting the building into the largest possible segments, panels, that still fit onto a flatbed truck so that we can then bring these panels off-site as quickly as possible. And that's the way we overcame this time limit. So it took us 5 days on site to take down a, what is it in square meters? So a 4,500 square foot building, 13 bedrooms, so quite a large structure on the residential scale. And what you can see on the image is how we basically lift these panels off with a forklift. And so at the end of the 5th day, we had the whole building stacked in these panels at a local reuse center, a facility that we used for the post-processing of these materials. And then over the next months, this process was done indoor in a warehouse under controlled conditions, which was really important because at the time we did this project, we had something like -10, -15 degrees Celsius on the construction site. The first day, the engines didn't start. So it's actually a really benefit of panelized deconstruction to move the majority of the labor into the controlled environment of a warehouse. So the study that we did has a scope that essentially starts with the demolition and deconstruction of 2 reference buildings, and then includes the processing and the salvaging of the materials that came out of it, and compares the economics, the labor, and the carbon of deconstruction versus demolition. And so if we walk through this in the reverse order, then what you see here is sort of the comparison of the carbon, embodied carbon. And you see that if the top slide looks at mass, so the landfill mass in the demolished project was roughly 120 tons. And the difference with the deconstructed building is actually not that large, because most of this comes, as you probably imagine, from the foundations, from the concrete. And so the timber part, everything above ground, in weight has not that big of, doesn't play that big of a role. But of course it is a big volume, and it is a lot of carbon that is in there. And you can see that the dimensional lumber and the hardwood flooring play the biggest difference in this respect. If you then look at the carbon savings, the all of the materials that were reused end up basically with about 8,000 tons of CO2 equivalent in direct savings, and then the sequestered carbon is about 60 tons. That's the carbon. Maybe more interesting is sort of the labor question. And here we see a relationship that is also well known. That's sort of something that we hear from other projects as well, that a deconstruction and reuse project roughly has 6 times the amount of labor hours from a demolition project. We had something very similar to that. If you add this all up, we're having about 500 to 600 hours for the deconstruction, and about 50 for the demolition. And this includes the post-processing and the bringing the materials back into the warehouse, onto the market of the reuse, onto the floor of the reuse center for resale. And then in terms of the resale value of these materials, and like adding up all the costs, we're at about a $60,000 project for the deconstruction, and the demolition was at 24,000. And so that difference, if you take out the resale value, and the material sales brought in 26,000, right, from all the materials that we salvaged. So there's a $8,000 difference in these two, but what you see here is that the consulting services here actually were exactly $8,500. And this is something that we had to pay because we did it the first time. And so we brought in the #1 expert from Washington. Maybe some of you know Dave Benning, who was consulting us on this project. And the hope, of course, is the more often we do this, the more this knowledge is local. And so if we don't have to pay for consultancy services, then we're evening out in cost, which is the other criteria that the developer put on the floor at the very beginning of the project. And so this is a summary of all of these different aspects, which clearly shows the sort of deconstruction has of course, the much better environmental impacts, and that the higher labor cost also clear, but the cost and revenue balance each other out. And so the moment that's the case, right, the moment we are cost competitive and time competitive, we can actually talk about all those fantastic benefits that reuse and deconstruction bring to the table. The fact that it creates local jobs, it's a benefit, right? The fact that we're saving history, not only carbon, right, but the history that's embedded in these projects, the knowledge and skills that are embedded in these materials, et cetera, et cetera. And so here's a couple of images from that process. I see Dave teaching us how to take down the house. And that's another big benefit of these projects, that you have the development of a green workforce, you have training of local trades. And so reuse really creates a very different new workforce locally here for us in Ithaca. And we're taking it even one step further now. These are my students from the architecture department. So we're regularly now organizing deconstruction workshops for architecture students. And the hope here is that once you've tried for a couple hours to take something apart that wasn't meant to be taken apart, and then you go back to the drawing table and draw a detail and design a detail for a new house, that knowledge and possibly frustration of taking something apart that wasn't meant to be taken apart leads to the design of different details that are designed for reuse, that are designed for disassembly. And so it's not just an exercise of how do we actually take a building apart, or how do we reclaim materials, what kind of materials can we reclaim, and how can we best integrate those back into the construction of new buildings, but also how do we design differently moving forward into the future. The project also taught us quite a few other things, and I'm just gonna sort of sum up this talk with a couple of outlooks into other pieces of the work that the Circular Construction Lab does. And one of them being a deconstruction survey toolkit. We call it Scanner, which is a little tool that uses commonly available LiDAR technology that most of us have on our phones or tablets, or some kind of hardware that we carry around. We have access to those. Combines it with a simple Excel sheet, and in that combination generates material quantities of buildings very quickly. So it's this kind of 2-3 hour process. And of course, these are ballpark figures using archetypes that we're attaching to surfaces. But the benefit is that we have a much more informed conversation about what could be. Ithaca is interested in this as a means to inform their permitting process. So there's many different possible avenues of a little tool like that to make the process simply more data-driven and a little bit more informed in terms of decision making. We're also applying this to a digital twin of the whole city. So now we're talking 6,000 buildings to understand material flow across the city, combine sort of different typologies of buildings, group them, figure out what could be strategies for decarbonization. Ithaca is one of the most progressive decarbonization strategies in the US. And so all of these 6,000 buildings are going to be electrified, for example, in the next couple of years. And so what does it mean to bring down the load demand of this electrification through weatherization, through reuse, through deconstruction, and a really careful look at a holistic strategy for the decarbonization of our cities. And none of this works without policy development and code. And so we formed a coalition, which is called CROWD. CROWD is an acronym for circularity, reuse, and zero waste development, and is a group that is rather active in central New York now. And one of the things that CROWD produced is a sort of policy guide. Here you see a template ordinance, deconstruction ordinance, and it actually was used just recently by the city of Auburn, New York, that just passed a deconstruction resolution using our template. And this is, as far as we know, the first policy of this kind in New York State. And so this is a really interesting development and a fantastic first step in the right direction. CROWD is also questioning the metrics that we're applying, especially when we're focusing so much on embodied carbon. What does it mean on the policy level? And so what we just recently published together with the with CNCA. CNCA is the Carbon Neutral City Alliance, is a guide on embodying justice. So can we embody justice as a metric similar to embodied carbon when we talk about circularity, when we talk about the policies and politics behind urban planning and permitting processes. And just to kind of I've mentioned it a little bit, sort of the how do we build differently? How do we move to the future with these materials? I wanted to show another little project that we actually built with the materials that we salvaged from Catherine Commons, so the project that we deconstructed a couple of minutes ago. And so this is a small structure. It's just a kind of an art piece for a biennial here at Cornell University on the art squad. But it is large enough to require a full building permit and a full structural analysis. And that's what made the structure so interesting to us, because it is the first time we needed a building permit to work structurally with salvaged timber, which is something that is not allowed in New York State, and actually in 50 of the US states. There's only 2 that have a policy for this at the moment, which are Seattle, Oregon, and Washington State. And so in this analysis and the conversations with structural engineers and trying to figure out how do we actually get a permit, what do we need to get a permit to reuse timber structurally, we discovered quite a few little points in the process where more research is required. And so that's some of the things that the lab is now engaging in quite successfully, actually, since this project. But the project itself sort of led us to understand these processes better, the post-processing, but also the understanding of the aesthetic values and qualities of salvage timber, or the values of a newly edited surface next to an unedited surface. So how can we work with these contrasts of old and new successfully in architecture? But then also, how do we connect the digital and the physical? What you see here is our material passporting system, where we know exactly where was the beam in the Catherine Commons project, where is it now in this project, how was it edited, what was done to it, and where could it possibly go next, right? And so with this knowledge and this kind of continuous chain of custody, we have a better idea of how to treat these materials, but also what are they capable of and what has happened to them in the past. On the right, you see a detail that of that structure, which really had to deal with the fact that we had incredible, and this is also not something new, right? We had incredible tolerances in the materials, because of course these beams and joists were partially hand sawn, partially machine sawn 120 years ago. And so the detailing of these materials in a new application needed to take all of this into consideration, because we didn't want to just plane them down so that they're done uniform so that we can use them, but we want to really play with the available material stock and the qualities that the stock brings as a starting point for a design process. And so since the project was designed for disassembly and designed for reuse, it has now moved. We just reinstalled it at Art Omai, which is an architecture and sculpture park in upstate New York near Ghent, so close to Albany. And it's reassembled in a different configuration because the site required different needs, different aesthetic qualities, but also different circulation. And that the detail that we developed allowed for that, right? So it wasn't a large shift. It was just basically a reassembly in a slightly different configuration. Something that has been important to me since the beginning of this process, and we've talked a little bit about metrics already, is how do we evaluate this? How do we evaluate this in the design process? And so especially for our students, but now increasingly also for the industry, we developed a tool which is called Rhino Circular, which is a little plugin for Rhinoceros 3D that basically in the drawing environment constantly evaluates circularity and publishes a material and building circularity report. And so every design decision leads to a re-evaluation of those numbers and gives immediate feedback to material choices or to detail connection choices. And it's a really interesting way to use circularity as a design tool and not just as a means to create a material passport at the end for a future use, right? So how can we design more circular is I think an equally important question in this holistic approach. And to end this, I mentioned that we need policy, but we also need code. So something that we realized in the redesign of the structure is that we're running on many different places into questions of what is allowable today. On the right-hand side, you see the connection detail of this little sculpture. And it's essentially just a T that has a couple of screws in it. But when we wanted to take it apart and put it back together, the structural engineer was not able to basically calculate what it takes to take a screw out and put the screw back in, because that doesn't fulfill the requirements of the code and how we would calculate this connection, right? And so we did a lot of tests to figure out, can we unscrew and rescrew a connection, and how would you then calculate that in terms of structural engineering? Or how can we reuse salvage timber in a kind of engineering way where we apply several layers, like a glue lamp, for example, as an example, but without the glue. So what is a design for disassembly glue lamp beam? So these are the questions that drive us right now in deciding how can we further the application of salvage timber into current building practices. And this is something that has been taken up by New York State finally. So there's 2 bills right now in both the Senate and the Assembly that we've been able to advise on, that basically take Washington and Oregon as an example, simply as at least applying a minimum structural grade to salvage timber, so that there is a route into a structural use for all of these materials, and to overcome the current practice, which is great, right? But I think there's so much more potential than using salvage timber decoratively if we were to find a way to actually apply it structurally. These books were mentioned in the introduction. We publish wildly, and hope that this helps. And I'm really curious to have a conversation. And with that, I'm ending it here.